This is STA 381, Chapter 7, Section 2, Sampling Distributions and the Central Limit Theorem. Okay, everyone, welcome back. We're setting the stage again. This chapter is kind of our bridge chapter between the first part of the course and the second part of the course. So it's just as you can't get across a large river without the bridge or knowing how to swim, we need this bridge. So again, you got to pay really close attention to these sections in Chapter 7. All right, so what we're going to be talking about is that something that we set the stage for last time, which is sampling distributions of a statistic. So we're going to talk about that, look at a fundamental theorem that we have in statistics that addresses that, and kind of see how it all works. Okay, so let's get started. All right, so we've got some definitions, and we're going to take a closer look at those. Random variables x1 up to xn are a random sample of size n if the x sub i's are independent random variables and every xi has the same probability distribution. So they have to have that same distribution. They have to be independent. So just as a reminder, independence means the outcome of one does not affect the outcome of the other. So just a basic idea of flipping a coin. You flip a coin one time, you get heads. It doesn't affect what the next coin flip is going to be. Same idea as with a random sample. Just because you picked a particular person from a population, that's not going to affect what the next person is going to be, or the next component if you're picking components. A statistic is any function of the observations of a random sample. So that's a reminder from last time. And the probability distribution of a statistic is called a sampling distribution. And that's kind of the fundamental part of this section. Okay, so first of all, before we even get to that, there are three distributions going on. And it is really important that you keep track of the fact that there are actually three distributions and that they are going to look different. There's the population. So it's our overall population of, let's say we're looking at a particular component produced on an assembly line at some sort of manufacturing company within, say, a 2-week time period. That all of those components that are produced within that 2-week time period, that is, and you're taking a variable measurement on them, that's our population. Then, let's say we draw a random sample from that population of those components. That's our sample, and it has its own distribution. So it could be that, the lifetime of a battery in a population, overall, let's say, it has maybe a shape that looks like that. Well, just because the overall population has that particular shape, if you draw a random sample of, say, 30 of those, and you look at that lifetime of the battery, you might have something that looks like that, because you're just drawing a sample of so many out of there. Say you're drawing 30, and it's not going to look just like the population. We'll see from there, and these are all of our little x sub i's. All we're doing is taking each component, say it's a battery, measuring its life of the battery and marking it down. A sampling distribution, let's say we're looking at, for x bar in this case, we would take many samples, independent random samples of size n, and that could have been that 30 that I said a minute ago. And those many samples of size n, you calculate x bar and then plot all x bars in some sort of histogram, dot plot, something like that. And so that may end up having maybe a shape that looks like that. So you're going to have three separate distributions, and that is really key to understanding this particular section to take you into the next bit of the course. So let's look at an example using an applet. So I'm going to go over to this applet. It's called StatKey, and it's free. You can see the website logstat5.com/statkey. We use it in different courses, but it's free, standalone software, and I really like it for looking at sampling distributions. So we're going to look at sampling distributions of the mean, and what we're going to do is simulate what I just said. Okay, so here we have, let's take a look at NFL contracts. So we have some preloaded data sets here. I'm going to click on NFL contracts, and so you can see the data table. And so this was in 2015, and you can see, and it's sorted from highest to lowest, yearly salary, Aaron Rodgers, Ben Roethlisberger, he makes a lot of money, all the way down to, at the very bottom, Everett Thompson at not even quite a $500,000 yet, so about $405,000. Okay, and so that population is over here in the upper right-hand graph. So it's just a dot plot, and if you hover over any of the pieces, you can see. If you want to investigate this dot plot. But you see it's highly skewed. So we have many people, a lot of people who are making around this 0.4, 5, 8, and so on, all the way up to here. But then we have, you know, the top two that are up here at the top. And so clearly that's the population. That was all players in 2015, what their salaries are. Now let's say I want to take a sample. I'm up here at the top. I'm going to choose samples of size 10. Okay, so if I just, and so what this is going to do is it's going to generate a random sample from this population of size 10 and then calculate, show me the sample and show me the mean. Okay, so down here in the lower right-hand box, this is the sample. So here we have the population distribution at the top right-hand box. Lower right-hand box is the sample distribution for that sample. It only took 10, and so it doesn't really have any kind of shape. We just have a bunch of values down here at the bottom. But then we see the sample mean right here in the very large box. So we have a sample mean of those 10 of 2.193. Well, that's just one sample. If we're going to generate a sampling distribution, we need to take many, many samples of that size. But I'm going to do this a couple more times so you can see what happens. I took a second random sample of size 10. There it is down here, again, not looking like much because we only have 10. But notice this time the sample mean was a little bit over 1, a little bit over 1 million. I'm going to do this a couple more times. Third sample mean. Fourth sample mean. But notice this part, this fulcrum right here, that's the mean of the sample means. Now, before we get to the rest of this, notice up here in the upper right-hand box of the population, we have 2,099 players, and we have the mean salary is 2.238. Median of 0.845 and a standard deviation of 0.3066. Here, down here, we see also similar numerical summaries. We have a mean of 1.202. That's our point estimate. That's our statistic. And we see that it's pretty far off of that population mean, and that's just going to be the way it is, especially with such a small sample. And we'll talk about how to deal with that issue later. And then we see a median and a standard deviation. Finally, up here in the large box, we see that we've taken 4 samples. The mean of all those sample means is 1.74, and the standard error is 0.723. Notice that's not equal to any of these other values, and that'll become important later. All right, well, we're kind of tired of doing this one by one, so I'm going to click on this and generate 5,000 samples. Actually, a little bit more than 5,000 samples. It's thinking now, I think. Okay, I may have actually clicked it 6 times. But what you see now is the mean of, so we see what this is a sampling distribution. All of these dots in this large graph, these are just sample means from each time a random sample of size 10 was chosen. And so we can hover over them, and then you can see over in the right-hand box all the sample distributions come up. But this is the sampling distribution of the mean, of X bar. This is a sampling distribution. Now, is it an exhaustive one? No, because I only took 5,004 samples, and that's not all possible samples of size 10 from a population of 2,099. You could do the math, but there's going to be a lot more than that. But this is giving you an idea of the shape. Population distribution, sample distribution, sampling distribution of X bar. Okay, but you notice it's still pretty skewed. It doesn't have the same shape as the population, but it is still pretty skewed. Now what happens if I change my sample size? Let's say I change it to 30. So we have to start over. Let's go ahead and generate 5,000 samples of size 30 now. And what do you notice? You notice that this shape, although still has some skewness over here to the right, looks a lot more normal. So normally distributed, not normal as in normal versus abnormal, than the previous one. And so that's worth noting at this point because that's an important component. But we still have some skewness here. Well, what if we change this from 30 to 60? Draw our 5,000 samples. So now we have 5,000 samples of size 30, or size 60, excuse me, from this population. And so again, here's our population distribution, our sample distribution for that last sample, and our sampling distribution of the sample mean. Now, notice that, again, less skewness going over here to the right, more of a normal type shape. So I'm sure at this point you can guess that as we increase that sample size, we're going to end up with a distribution that looks more and more like a normal distribution. And that is a fundamental point in going forward to the next couple chapters, because the fact that this distribution is approximately normal for the sample mean means that we can use all of the theory that accompanies a normal distribution and take it and run with it in trying to do like confidence intervals and hypothesis testing, basically trying to do some more inference with our sample point estimates. Okay, so let's formalize this. If x1, x2 up to xn is a random sample of size n is taken from a population can be finite or infinite, with a mean mu and a finite variance sigma squared. These are all conditions that are actually pretty important. And if x bar, capital X bar, is the sample mean, capital X means, or x bar or x means that this is a random variable, then the limiting form of the distribution, and this is our z, this should look familiar. Remember z in earlier chapters, standard normal was x minus mu over sigma. This looks pretty familiar. Then the limiting form of the distribution, x bar minus mu over sigma over the square root of n, as n gets very large, is the standard normal distribution. Now, what does that all mean? What that means is that the distribution of x bar, and all we're doing is we're just recentering it and rescaling it. You know, we recenter it by subtracting off the mean. We rescale it to have a standard deviation of 1 by dividing by x bar's standard deviation. Because it has a different, we're not using sigma here because we have x bar here instead of x, and so we have to divide by the square root of n. But what we see here is that this distribution of x bar is going to be approximately normal as n gets large. So if you're thinking ahead, and this is called the central limit theorem, it's kind of like the remember the fundamental theorem of calculus? This is kind of like our fundamental theorem of calculus, and we call it the central limit theorem. It was discovered and developed by Carl Gauss. So you're familiar with Gauss for many, many things, many, many contributions to the field of mathematics and statistics. And one of his most notable items was through the central limit theorem. All right, so as n gets to infinity, or n gets very, very large, you might be wondering, okay, what's the definition of large? Well, that depends. As a general rule of thumb, we say that if n is larger than 30, then that's okay. But you probably noticed in our last example with the NFL salaries that 30, in that case, samples of size 30, still had, that sampling distribution still had that right tail with a little bit of skewness in it. So if you have a skewed distribution or some extreme outliers like we did, then you need to make that number, n needs to be larger. And what am I, and it really does depend. I would say at least 60 or 70. So keep in mind that, and if you have even more skewness than we saw, you might need to be going up to samples of size 100 before you can reasonably say that the distribution of x bar is approximately normal. So as I said, this is pretty important, and it has to do with our sampling distribution. So this is talking about the distribution of x bar. That's what's changing as we get more and more information into our sample. The population distribution does not change, and the sample distribution changes from sample to sample. But what's changing here is the sampling distribution of our statistic, x bar in this case. Okay, so let's go back over to StatKey for a minute and investigate what happens with the mean and standard deviation. All right, so let's go ahead and go back to this example. Let's leave this at 10. And so what I want to note is what happens to the mean and standard deviation of the sampling distribution. So we'll go ahead and generate 5,000 samples of size 10. And we notice that the mean of all the sample means is 2.235, pretty close to the population mean. The standard error is 0.985. That's smaller than the standard deviation. If you remember on the slide, remember it was x bar minus, let's see, let's go down here for a second. X bar minus mu over sigma over the square root of n. This sigma over the square root of n that's our standard error that they're talking about. So they're taking, to estimate it with simulations, you look at the population standard deviation sigma and divide by the square root of 10 in this case. Okay, so to get back over, I'll just open a, well, no, let's open another window. Oh, wrong. There we go. Let's do that again. Okay, so this 0.965 should be very close to 3.066 divided by the square root of 10. So make a mental note of that, or write it down, and then we'll come back to it because we're going to change our sample size to 30. So remember, now our samples are getting more information in them. Okay, so now again, sample mean, or mean of all the means is still pretty close to the population mean. And that is true, is that the mean of the sampling distribution in theory will end up being the mean of the population. So it's really, really close now. If we were to be able to take all possible samples, it would be exactly the same. And then notice that this is shrunk because this value, 0.548, is a square root, is 3.066 divided by the square root of 30, or approximately, because we're simulating. All right, let's do that one more time and look at 60. Okay, again, standard error has shrunk. This mean is a little bit different this time. Again, that's sampling error. That has to do with the fact that we're simulating our results here, so we're going to have a little bit of error. And our standard error here, again, should be approximately 3.066 divided by the square root of 60. So the spread of our sampling distribution is shrinking because we're getting more information into each sample, and so there's going to be less variability. Here's something to just kind of think about, is that sample means will have less variability than just your observations. So we should see this continue to narrow, and you can play with this if you want, as you get larger and larger samples. Okay, so let's look at this maybe in a different way rather than from simulations. Suppose we have a random sample or random variable x has a continuous uniform distribution, and its distribution is here, and this is our population. So it's 1/2 from 4 to 6, 0 otherwise. Find the distribution of the sample mean with a random sample of size 40. So our 40, now just to kind of remind you of what a uniform distribution looks like, it's really just a rectangle. So we don't have to worry about any skewness or outliers with this distribution. That's what it looks like, so an n of 40 is sufficient. By the central limit theorem, x is going to be approximately normal, and I would say approximately normal. It's not exactly normal. And so we see it has a mean of 5. The population variance is 1/3, and then this is sigma squared of x bar. This is the variance of the sampling distribution of x bar. And then we see the pictures right here. We can clearly see right here we have a uniform distribution, and now we have a really close, it looks exactly normal at this point, and then this is our standard deviation. Okay, so what about if we have like a difference in sample means? Does this also apply? And the answer is yes. It's going to apply to a difference in means, a difference in proportions. It applies to many statistics, not all of them, but it does apply to many statistics. So if we have two independent populations, and that's important, mu1 and mu2, variances sigma 1 squared and sigma 2 squared. If x1 bar and x2 bar are sample means from these two independent populations, then the sampling distribution, and this is our sampling distribution that we standardize by subtracting off its mean, dividing by its standard deviation, is approximately standard normal if the conditions of the central limit theorem apply. Now, if the two populations start off as being normal, then the sampling distribution is exactly normal. If they start off as something else, we still have to have, in this case, N1 and N2 both being at least 30. Some textbooks may say 40, by the way. And then, again, if you have skewness, we're looking at least 60 or 70. Okay, so I wanted to just point you back to the video solutions that are in Wiley Plus. Notice that in this chapter, we have all of these video solutions for all of these problems. So there's several problems from sections 2 3, 4, and 5 or that's not 5, that's an S, that give solutions on video to problems. So go back and look at those. Really make use of the resources in Wiley Plus. Notice that there's also down here video lessons, additional example using the central limit theorem to determine a probability involving 2 sample means. There's data sets there. There's flashcards down here. So I can't emphasize enough how valuable having all these additional resources are. So please make use of the resources as much as you can, especially in an online environment where you're not really face-to-face with your instructor or face-to-face with students. This will really help you a lot. All right, so to sum up, we talked about the central limit theorem. We talked about how important it is. So just remember that idea is that it's the distribution of the sample mean that actually changes as your sample size gets larger and it becomes virtually a normal distribution. Okay, that's the conclusion of the lecture.